Rate law is an equation expressing the rate of a reaction in terms of molar concentration of the species involved in the reaction. And the rate is often found to be proportional to the molar concentration of the reactant raised to a simple power, and this power we call order of reaction. So let us see this rate expression here. So rate equivalent to K square bracket A to the power of M square bracket B to the power of N. So M and N here refers to the order of reaction, whereas the A and B in square bracket refers to the species involved in the reaction, and square bracket means molar concentration, and K here is constant. So M plus N is called overall order. So let us look at this reaction here. Okay, so reactant A and B, okay, react to produce products. Okay, and small letter A and small letter B here is referring to the stoichiometric value of the reaction. So when we write the rate law expression, this is how we write it. Okay, note that M and N here is the order of reaction, not the stoichiometric value here. Okay, not the stoichiometric value of A and B. Okay, it's a totally different thing, M and N, like I have explained in my previous lecture. Okay, this one comes from the experimental value. Okay. So at constant temperature, the rate of a reaction is a function of concentration of reactant or products. And the rate law of a reaction cannot be determined from balanced chemical reaction. Like I mentioned just now, the M and N value is not referring to the stoichiometric value small letter A and small letter B. Okay, it can only be determined by experiment. Okay, can only be determined experimentally. So the rate law provides concise expression for the cause of reaction. Okay, and it helps in calculating reaction times, yield, as well as optimum condition. Now consider this example here. Okay, just now is very general example. Now we look at the real example. So reaction between amino acid tyrosine, okay, and iodine will give you this rate law here. Okay, so classify it by order. So order means the power of each of these species here. So because no number is written here means first order for tyrosine and also first order for iodine, and the overall order is second order because 1 plus 1. Okay, now the rate constant of a chemical reaction is a measure of the rate of reaction when all the reactants are at unit concentration. Okay, so rate equivalent to K times function of concentration of reactant, like just now. Rate equivalent to K species A times species B. Okay, so K here, okay, is referring to the rate constant. So if concentration are equal to unity, means the rate of reaction K, where K is rate constant or rate coefficient. Now the rate constant K depends on the nature of reaction and temperature, and normally K value will increase with temperature. And the rate constant is a characteristic of chemical reaction, so it is a numerical measure of how fast a reaction can occur. And if mole per liter is used, unit for the rate constant would be depending on the order. Okay, so if we have mole per liter over mole per liter power of n times s, okay, where n is the total order of fraction. So if first order, unit of k will be per second. Okay, first order means this one is 1. Okay, so mole per liter over mole per liter you can cancel off, so leaving behind per second. So the unit for k is per second. Not that for kinetic the constant will have a unit. Okay, not only rate law or concentration, but constant will also have unit. Now if second order means this n value is 2, so we can cross this, leaving behind 1 here. So the k value would be per liter per mole per second, or we can just write per molar per second. Okay, you can understand this better when we look at the following example. Okay, let us look at this exercise here. Okay, reaction between nitrogen oxide and hydrogen gas will yield nitrogen gas as well as water vapor H2O. Okay, experimentally found to be first order in hydrogen and third order in nitrogen oxide. So how can we write this rate law? Remember, the rate law is depending on the reactant. Okay, so how to write the rate law? So rate is K, concentration of nitrogen oxide and also hydrogen. First order in hydrogen, third order in nitrogen oxide. So this is the right rate law. Now let's look at the answer. Okay, question B. What is the overall order of the reaction? Overall order means here, total power here plus total power here. Okay, so overall order is 4. Okay, fourth order. Okay, let us check our answer. Okay, fourth order. Now question C, what are the units of the rate constant? Okay, so you are asked to find the unit for this rate constant K, given the rate is in molar per second. So what is the rate here? Okay, so molar per second equivalent to K. This one is molar, this one is molar cube. Okay, so here we get K times molar power of 4. Here is molar per second. So to find K, we bring this over here. Okay, so this one cancel, leaving this behind with 3. So the rate constant will be K per second per cubic molar. Okay, so let us check our answer. Okay, yeah, right. So this is example of balanced chemical equation or reaction and the rate of expression. Okay, the rate expression. So remember, I have mentioned that the order of the reaction is not the stoichiometric value of the reaction. So look at the first example here, as if the order is similar to the stoichiometric value. Okay, so this we call as coincident. Okay, reaction between hydrogen and iodine producing hydrogen iodide gas. Now let us look at the second one here. Okay, pentoxide here. Okay, so the order is 1. Okay, so you see stoichiometric value is 2. Okay, the third example, okay, the third one, nitrosyl chloride. Okay, coincidentally, the stoichiometric value is the same as the order here. Okay, 2. And the last one is, okay, trichloromethane. Stoichiometrically 1 trichloromethane here with 1 chlorine gas, but look at the red law here. Okay, trichloromethane 1 stoichiometrically is coincidentally same as the stoichiometric value 1, but chlorine here is half. Okay, stoichiometric value in the reaction is 1. So this shows that the red expression can only be determined through experiment. This value are obtained from experiment, like in my previous lecture when I explained on different set of reaction. Got set 1, 2, 3 and 4, so on. Elementary reaction is one whose mechanism of occurrence is just what is written in the reaction equation. So if you go back to physical chemistry 1 that you have studied, and look back on Hess law. Okay, Hess law is a sequence of a step in order to get the overall reaction. You have step 1, what is the reaction occurring in step 1, what is the reaction occurring in step 2, and then you find and you've deduce the overall reaction based on the step 1, step 2 and so on. Each of that steps is categorized as elementary reaction, and when you write the red equation for that elementary reaction, it is based on the stoichiometric of the reaction itself. Okay, for example, if you have step 1, okay, let's say step 1, the reaction is let's say bromine. Okay, bromine gas and also nitrogen oxide gas to give bromine NO gas. Okay, then step 2, we have Br 2NO gas and also NO gas to give 2 BrNO gas, and the overall we have Br2 and 2NO gas, 2 BrNO gas. Okay, so when you write the rate equation for step 1, so rate is gonna be K Br and NO, and for second step rate, okay, second step elementary reaction, the rate is K Br2 NO and also NO. So we follow the stoichiometric reaction of each step. Okay, so that is rate equation for each elementary reaction. So this elementary reaction involve only one or two molecule. Okay, one or two molecule means you can have reaction A plus A to give you product. Okay, or A plus B to give you product. So that's why it means it can involve only one or two molecule. Okay, one between the A molecules or two, A and B. Okay, to give you product. Okay. So the term elementary reaction seems to be conflict, especially with kinetic order, because kinetic order can only be determined experimentally and cannot be deduced from the coefficient of the balanced chemical equation. However, molecularity, yes. Okay. It represents the stoichiometric value to use to balance the chemical equation, and that is why um, when we say elementary, it comes together with the word molecular. Okay, so we can have unimolecular elementary step or bimolecular elementary process. So molecularity of a reaction refers to a particular elementary reaction, okay, which I mentioned just now. Okay, so the order of reaction is empirical quantity, which follow from experimentally determined of Red law. So that is order of reaction. Okay, so elementary reaction Red law can be written based on the balanced chemical equation. So molecularity of an elementary reaction is the number of molecules coming together to react. Okay, so elementary reaction may be unimolecular or bimolecular. Okay, unimolecular means only one single molecule. Okay, with in which it can shake itself apart to form a new arrangement of its atom. Bimolecular means two molecules colliding with each other and undergo some changes. Okay, so bimolecular, it can be from two same reactant. For example, you have A and A to give product, or you can have A plus B give product. Okay, so that is bimolecular. There is another molecular reaction which is thermolecular. So thermolecular will involve three molecules. Okay, thermolecular. Okay, this one involve three molecules that have to collide with each other at the right time. Okay, but it has low probability because to get these three different reactant to collide with each other at the same time is rather impossible. Okay, so normally thermolecular reaction involve two different molecules, and another one another one is in high concentration, for example solvent. One example of thermolecular reaction is between oxygen molecule and oxygen atom in the atmosphere with that 70% nitrogen to give us ozone in upper atmosphere. Okay, so one example is oxygen atom reacting with oxygen gas in the presence of nitrogen gas in the upper atmosphere to give us ozone. Okay. So the function of nitrogen here is to absorb the energy between the reaction of these two. Okay, so that's why besides the ozone, it produces energetic nitrogen gas. Now another molecular reaction is 4 molecules collide with each other, but it is never proposed because third molecular is considered very very low, what more 4 molecules. So that's why reaction with more than 3 molecularity are never proposed. Alright, how do we write red law for elementary reaction? So let us look at one example here. Okay, the reaction between hydrogen and bromine to produce hydrogen bromide and also bromine. So this reaction is bimolecular, okay, because 2 different molecules. So therefore, to write the red law, okay, K square bracket H, K and also square bracket of bromine. Okay. So bimolecular reactions are second order because this is first order, this is first order. So overall order is 2. So second order. Okay. But it is not the case that second order reaction are necessary bimolecular unless they are elementary reaction. Okay. Like I mentioned in the earlier slide, bimolecular reaction can comes from same molecule reacting with each other. For example, A plus A just now, okay, giving product. So when we write the red law, okay, read, we have K, A, second order. Okay. So unimolecular reaction are first order. Okay, so if we look at this reaction here, A producing intermediate to give us the final product here will have 2 different rate constant, K with regards to A, which is the reactant, and for P product, the reactant would be the intermediate here. So we have another rate constant Kb. So to write the rate law, okay, this is the rate law. Okay. Okay, let us look at general reaction here. So A, B, C reactants produce P, Q, and so on. So the rate law is based on the reactants, and note that we have X, Y, and Z here referring to the order, kinetic order of the reaction. Okay, not the stoichiometric. Okay, unless this is elementary reaction. Okay. So let us look at one example here. Okay, decomposition of hydrogen peroxide. So to write the rate law, okay, is based on the reactant here, and this is first order. Okay, based on the experiment condition or experiment value. Okay, it's in first order. Another example here. Okay, acetaldehyde. Okay, so the red law here is based on acetaldehyde. Okay, this is second order. Okay, coincidentally, this is the same as the stoichiometric number, but it does not come from this. So this is deduced from experiment. So this is another example, reaction between nitrogen oxide and oxygen. So the red law is red K and O 2 and O2 1. So second order with respect to NO and first order with respect to O2. So the overall order is third order. So very seldom that reaction of more than three order exists. Okay, but there are order of reaction that exist as fraction or even zero order. Okay, so for example here, so acetaldehyde here. Okay, so the order for this is in the fraction 3/2. Okay, so another order reaction is zero order. So zero order is reaction which is independent of concentration of the reaction. Okay, so consider the reaction between nitric oxide and oxygen here. Okay, so the rate is written as nitric oxide concentration and also oxygen. So the order of the reactants here is 2 for nitric oxide and 1 for oxygen. In this order of reaction, or this value here, is obtained from experiment, not from the balanced chemical reaction. Although coincidentally it looks like it, but it's not. Okay, it's determined experimentally. So the overall order for this is third order. Okay, 2 plus 1. So this is the explanation. Okay, so 2 for M and 1 for N just now. Okay, so when we conduct the experiment, okay, we have different set. Okay, like I have explained in my first part lecture of kinetic. Okay, part 1A. Okay, so we have different set of experiment. So let's say in set 1, okay, and set 2. So in set 1, the concentration of nitric oxide is the same as in set 2. Let's say we put 0.1 molar. Okay, but the concentration of oxygen double. Okay, double. So this is referring to NO. Okay, so this is oxygen. Okay, so double 0.1 0.2. Okay, so when we write the ratio, okay, the rate obtained from set 1 and the rate obtained from set 2, okay, this is what we get. Okay, experiment 2 and experiment 1. Okay, so this one constant, concentration of oxygen double, so you have 2C and C here. Okay, so we can cross this and we can cross one of the C. Okay, and we have 2 here. Okay, so when oxygen is double, the rate will also double. That's why it's first order. Okay, Now let us look at another set of experiment. Okay, oxygen is now held constant. Now nitric oxide is double. Okay, double. So the rate law will predict the rate will quadruple. Okay, so we write the rate for each set of experiment. Okay, for oxygen constant, for nitric oxide double. Okay, so you have 2C here and C. Okay, don't forget 2. Okay, so we can cross this. Okay, this is 2C squared and 1C squared. Okay, so we can cross one of it. Okay, leaving behind 2 to the power of 2. Okay, 2 to the power of 2 means 4. So quadruple. Okay, so this come from 2 power of 2. So that's why the red order is 2. Okay, so the rate is proportional to the square of nitrogen oxide square. Okay, order of reaction 2. So the experiment conducted is categorized as isolation method. If one of the concentration of one reagent double while the other one remain constant, okay, and if the rate is found to be unchanged, okay, let's say you have reactant A and B to give you a product. Okay, one is held constant, another one is double. Look at the rate. Okay, if the rate remains the same, then the order is 0 with respect to the changing reactant. If the rate observed is double, then the order is first order with respect to changing the reactant. If the rate of the reaction is quadruple, then the order of the reaction is second order with respect to the changing reactant. Okay, like the previous example just now, we have double, we have quadruple. Okay, this is exercise that you can try. Okay, finding the rate of reaction with respect to carbon monoxide CO and nitrogen dioxide NO2, and these are the set of experiment given as well as the rate for each set. So this is actually set 1, this is set 2, set 3, 4, 5 and 6. So this is the rate for each set. Okay, so based on this experiment, identify the order of reaction with regard to CO and also NO2. Okay, follow the example that I have explained earlier. Alright, how do we determine rate law? The method used is initial rate. So method of initial rate actually measure the rate at the beginning of a reaction for different set of different initial concentration of reactant. Okay, let us look first at single reactant. Okay, like in this example here, this is example of unimolecular reaction where we have one reactant to give us a product. Okay, so the reaction rate is directly or linearly proportional to the concentration of the reactant. Okay, and that will give you first order. Okay, if you double the concentration of the reactant A, the rate should also double. Okay, if you half the concentration of reactant A, the rate also should half. So that is first order. Okay. Now for second order, the reaction rate is proportional to the square of concentration reactant A. So if you double the concentration of reactant A, the rate should quadruple. Remember, 2 power of 2. Okay. So if you halve concentration of reactant A, the rate also should change by quarter. Okay, let us look at example solving the rate law using method of initial rate. Okay, so this is a reaction which depended on the concentration of substance J. Okay, so we have set 1, 2 and 3 here at different initial concentration and their respective rate. Now the question is asking for the order of the reaction with respect to substance J and the rate constant K. So how do we solve this question? First of all, we need to write the rate law expression. So the rate law expression for this is K square bracket J power of N. So N here is the order of reaction. Okay, K is the rate constant. Now, we are given the data here, so we analyze the data here. Okay, so if we double the concentration of substance J, look what happened to the rate. Okay, the rate is not double but quadruple. Okay, so if we double this, we get 0.03, and if we double 0.3, we get 0.03, we get 0.06. So twice. Okay, so that means double concentration, rate quadruple. Okay, so when the rate quadruple means N, okay, the order of reaction will be second order. Okay, remember 2 power of 2 is 4. Okay, second order, quadruple. Okay, so we have solved the first question, which is the order of reaction, which is 2. Okay, 2, second order. Now, let us solve rate constant K. Okay, so how to find K? Okay, first we select any set here. Okay, any set here. Let's say we go for the first set here. Okay, so the first set here, the rate is 0.015 molar per second. Okay, K concentration is 0.1, order is 2. Okay, so we can solve for K. So remember, this is 0.1 molar. So squared means molar squared. So we have 0.1 squared is 0.01. Okay, 0.01 molar squared. Okay, so this one bring over here. So here to solve K. Okay, so it means 0.015 molar per second divided with 0.01. So we cancel molar, leaving behind per molar per second. So you see here, final answer is per molar per second, and K is 1.5. Okay, so 1.5 per molar per second. So that is method of initial rate. Okay, next we look at integrated rate law. Okay, so the concentration of reactant A as a function of time can be equated to the rate law. Okay, R equivalent to K square bracket A power of N. Okay, or we can write this like this. Okay, it's the same. Okay, it means the same thing. Okay, So let us move on to zero order kinetic. Okay, so if you remember, the definition for zero order kinetic is independent of concentration. And let's say we represent a zero order reaction as A producing B. Okay, so A reactant, B product. Okay, so we write the rate law. Okay, so negative d square bracket A over dt equivalent to k square bracket A power of 0, is zero order. And because concentration A power 0 is equivalent to 1, so we get k. Okay, so we get negative dA over dt equivalent to k. And then we rewrite this, we bring this over here. Okay, so we have negative dA equivalent to negative k dt. Now we integrate both sides. Okay, and between 0 and time t, okay, we get this. Okay, when we integrate. Okay, so when we integrate, we get square bracket at minus square bracket a naught equivalent to negative kt. And then we rearrange this so that we get a positive value for this. Okay, we bring this over here and this one over here. Okay, we exchange. So we have a naught minus at equivalent to kt. So this is the integrate rate law for zero order. Okay, question 2 here. So you must memorize this. Okay, so this is for zero order. Now, when we plot the concentration of reactant A versus time, you will get a negative slope here. Okay, you get negative slope here. Okay, again we rearrange the equation 2 just now, which is A naught minus E t, we get k t. Okay, so when we rearrange, we get equation we get equation 3 here. Okay, so the plot of A versus time, we get straight line, negative slope. Okay, here negative, this is referring to the slope. Okay, so this is zero order. Okay, so how to determine if a reaction is zero order? Okay, first step is to solve equation 2. Okay, for the rate constant k. Okay, so we rewrite back here equation 2, which is now A naught minus AT equivalent to KT. Okay, so that is equation 2. Okay, so we solve K. Okay, we solve K means we bring T over here. So A naught minus A T divide with T. So we insert A at various time T. If the value that we obtain is constant, means the same value, then it proves that the reaction is zero order. Okay, zero order. Okay, the K value has to be the same. Okay, let's say you have 3 different set. Okay, 3 different set of experiment. Okay, different concentration of reactant, okay, at different time. So we insert different time value and its respective concentration of reactant. So if we obtain similar value of K, means it proves that that particular reaction obey the zero law kinetic, okay, zero order kinetic. Now the unit for a zero order rate constant K are mole per liter time. Okay, time can be second, can be minute. Okay, so this is one example. Okay, mole per liter second. Okay, per second. So means molar per second. Okay. Now the second way to determine if a reaction is zero order is by using half-life method. Okay. So half-life method means the time for a reaction to go halfway. Okay, so that means T is T half. Okay, half. Okay, half. So that means the concentration A, okay, substance A at T half would be the initial concentration divided with 2. Okay, so that means equation 2 just now, which is anode minus AT equivalent to KT. Okay, so this AT would become anode over 2 here. Okay, T here will become half. Okay, T half. So we rearrange this, we solve this. So T half would be anode divided with 2K. Okay, so the half-life is directly here, half-life is directly proportional to the initial concentration of the reactant. Now the characteristic of zero order, okay, is summed up here. Okay, first one, okay, rate constant would be concentration over time. Okay, here. Okay, molar per second or molar per minute, molar per hour. Okay, so that is the rate constant for zero order. Okay, the unit for rate constant K. Secondly, the product concentration is directly proportional to the time. Okay, so when we plot this now, you get this negative plot here. Okay, so this is the concentration of the reactant over time. Okay, directly proportional. So this slope here will give you the K value, rate constant. Okay, so at any time of T and its initial concentration, the K value will always be the same. So that will prove that reaction obey the zero order kinetic. Okay, point number 3. Okay, the half-life of zero order reaction is proportional to the initial concentration of the reactant. Okay, so when X is equivalent to A over 2, T is T half. Okay, so A2 equivalent to K naught T half. So means half-life is proportional to the initial concentration of the reactant. So these are the example of reaction which obey zero order kinetic. Okay, so we have heterogeneous reaction. Okay, means the reaction occurring on the solid surface. Okay, for example, dinitrogen oxide on the surface of hot platinum wire, giving producing nitrogen and oxygen. Another one is ammonia on the surface of tungsten, producing nitrogen and hydrogen. Another one is hydrogen iodide on the surface of gold, producing hydrogen and iodine. So you note that the reaction here occur on the surface of catalyst. So these are the catalysts. Okay. So when the surface of this catalyst is saturated, means the amount of the absorbed gas is constant. So increase in pressure will not change the surface concentration. So that is why reaction rate is independent of the reactant concentration. Okay, so zero order is independent of concentration. So this is example of a zero order reaction involving two or more substance or reactant. Okay, and the rate will have zero order dependent upon one of the reactant concentration. Okay, for example, reaction between acetone here and also iodine producing iodoacetone and hydrogen iodide. So if we write the rate here, okay, this is the rate. Okay, rate is rate constant K with regard to concentration of acetone. So the reaction is first order in acetone but zero order in iodine. So you don't see iodine in the rate expression because of zero order. So therefore, the rate, okay, can be measured by monitoring the decrease in the iodine concentration. Moving on to the first order kinetic. So most reaction or many reaction will follow first order kinetics. Okay, so this is the general reaction of first order. We have reactant A producing product. So when we write the rate law expression, we have negative dA over dt equivalent to K cos square bracket A power of 1 cos first order. So we rearrange this rate law expression to give you this. Okay, so we bring this over here, dt over here. So that's why we get K dt. Okay, negative dA over A. So we take equation 1 here, okay, negative dA over A equivalent to K dt, okay, and then we integrate, okay, at time 0, t 0 and t, okay. So we have this ln A minus ln A naught equivalent to negative KD. So this is after integration of this rate law. Okay, so we rearrange this. Okay, we rearrange this. We get ln A naught divide with A equivalent to KT. Okay, and this is the formula you need to memorize. Okay, just now you should memorize for zero order. This is first order. Now if we plot, okay, ln A versus time, okay, in which we rearrange the equation 1A just now, okay, to give us equation 3 here. Okay, so we rearrange equation 1A. 1A just now is ln A naught, okay, divide with A, concentration, okay, equivalent to KT. Okay, so we rearrange this to give us this. Okay, so that we get the pattern for plot, which is y mx plus c. So that's why we get ln a equivalent to negative kt plus ln a naught. Okay, so negative k, so negative slope here. Okay, and this here is ln here is a naught. Okay, so this is a plot, okay, for first order kinetic. Okay, so you must memorize this plot pattern. Okay, for zero order just now, concentration versus time. This is first order, ln concentration rate then versus time. So how to determine if a reaction falls under first order kinetic? Okay, similar like we did for zero order. Okay, again we write the equation of 1a first. Okay, and then solve this so that we get k, so means we bring t over here, so we get 1 over t times ln a naught divided with a. Okay, so we insert a concentration at various time t. Okay, because it's just now it was ln a versus t, so we insert a naught at various time t. Okay, so if the k value we obtain is constant, then the reaction is first order. Okay, so the unit of the first order rate reaction, okay, is 1 over time. If zero order just now, concentration per time, right? Concentration per time here, so you can have molar per second. Okay, but for first order, okay, the rate constant is only unit of per time. So first order is, let's say, per second or per minute or per hour. So that is the rate constant value. Okay, for first order. So this is k, this is first order. Okay, so this is the unit for k value for zero order. Okay, the second approach is half-life method. Okay, similar like the zero order. Okay, so at time t equivalent to half. Okay, so the equation 1a just now will become like this. Okay, kt half. Okay, the a concentration at time t become a naught divided by 2. Okay, so we rearrange this. So solving for half-life t half, we get ln 2 divided with k. Okay, so solving ln 2 we get 0.693 over k. Okay, so half-life for first order is 0.693 over k. So the half-life here is independent of the initial concentration. No concentration involved. Okay, just k. Okay, constant. So this is example of reaction that falls under first order kinetic. Okay, so the composition of nitrogen pentoxide, okay, producing nitrogen dioxide and also oxygen. So this is example of first order. So the rate law expression is d nitrogen pentoxide over dt equivalent to k in 205 power of 1. Okay, first order. Note that the order is not the same as stoichiometric. Okay, so means this is not an elementary reaction. Okay, another example of first order processes are nuclear process. So you have studied this under physical chemistry 1. So all the nuclear processes obey the first order kinetic. Okay. Another example of first order reaction is decomposition reaction. Okay. So oxalic acid decomposed into carbon dioxide, and also methanol here. Okay, let us look at exercise to understand the concept better. Okay, so decomposition of nitrogen pentoxide just now. Okay, first order. Okay, so if initially 2.56 milligram of nitrogen pentoxide present in a container, and then after reaction occur for 4.26 minutes, only 2.5 gram remains behind. So what is the rate constant in unit of per second? So how do we solve this equation, this problem? Okay, first of all, the first step is to write the integrated rate law for first order process. Okay, so this is the integrated law for first order process that has been rearranged. Okay, so remember first order is ln A minus ln A naught equivalent to negative KT. So if you bring ln over here, so we have exponent E negative KT. So A at time T divided with A naught. Okay. So substitute the information given in the question inside the formula. Okay. Okay, substitute 2.5. Okay, dinitrogen pentoxide concentration at time T, and then the initial concentration, which is 2.56 milligram. So this is what we get. Okay. Okay, next we insert the value of T, which is 4.26 minutes, because the question final is asking for per second. So we have to convert this minute into seconds, so which is 256 seconds. Okay, so we bring the exponent back here, so become ln. Divide this first, then you ln. Okay, you don't ln separately, otherwise you get different value. Divide first, then you ln, and then we can solve for K, which is 9.3 times 10 power negative 5 per second. So next is pseudo first order reaction. So what does it mean by pseudo? Okay, pseudo means the reaction obey the first law kinetic, but it involves more than one species in the rate determining step. Okay, rate determining step. Okay, so this pseudo first order involve solvent molecule or catalyst as the additional reacting species. Okay, for example here, hydrolysis of methyl acetate. So you have two reactant here, and one of it is the solvent molecule. Or another example here, inversion of sucrose. So we have again solvent molecule. Okay, so that is pseudo first order. One of the species is in very large amount, okay, that we can um, ignore. Okay, so means the uh, the the red law is only depending on the other reactant. Okay, so when the water is present in large excess, okay, the concentration virtually remain constant. Okay, so that's why the rate of reaction will only depend on the other reactant. Okay, so in the case for the first example, the reaction will depend on the methyl acetate concentration. Okay, so this is the rate law. Okay, so this is the constant for water. So when we integrate, the new rate constant can be defined as this. Okay, K equivalent to B times K1. Okay, equivalent to 1 over naught ln A naught over A. Moving on to second order kinetics. Okay, so many reaction also falls under or follow or obey second order kinetic. Okay, for example here, hydrogen iodide producing hydrogen and iodine. Okay, so we write the general reaction for second order. Okay, we have return for the same product. So rate law expression is K A power of 2 for second order. So we integrate like we did for zero order and first order. Okay, so the integration from A to A naught at time t to t naught to t. Okay, so we have this, okay, integrated equation for second order. Okay, so you have to memorize this. If first order we have ln just now, right? Okay, so for second order is one fraction 1 over A minus 1 over A naught, equivalent to KT. So that is second order. Now when we plot for second order kinetic, we also would get a straight line, but now the slope become a positive slope. Okay, so the axis is 1 over reactant A concentration versus time. Okay, again we rearrange the integrated formula of second order so that it so that the um, formula is y mx plus c. Okay, for plot. Okay, so the slope here is k. Okay, this one here, k. Okay, now how do we determine a reaction falls under second order kinetic? Okay, similarly like zero order and first order, okay, we substitute the concentration of reactant at various time t into the integrated formula. Okay, if the value of the rate constant K is the same, then the reaction is second order. Okay, so the unit for the second order reaction rate, okay, is liter per mole per time. Okay, kalau zero order yang sebelum ni, dia molar per time, right? For second order, it's per molar per time. Okay. Now the second approach is half-life method, similarly like zero order and first order. Okay, so we substitute T, okay, to half-life T, and A at time T half become A naught divided with 2. So we substitute this into the integrated second order reaction. Okay, we get this. Okay, 1 over A naught divided with 2 minus 1 over A naught equal to KT half. So we rearrange this to solve for T half-life T. So we get 1 over K times A naught. So if you note this expression here, equation here, the half-life for second order is inversely proportional to the initial concentration. Okay, this is 1 over K A naught. Okay, inversely. Okay. Now this is the summary for the characteristic of second order kinetics. Okay, the first point is that the unit for rate constant is per molar per time. Okay, and the plot for second order is 1 over rate and concentration versus time, which give us a positive slope of K, so a positive value of K. The half-life for a second order reaction is inversely proportional to the first power of initial concentration. So these are the example of reaction which obey the second order kinetic. Okay, saponification of an ester is a second order reaction. Reaction between ethylene bromide and potassium iodide in 99% methanol is also a second order. Reaction between potassium persulfate and potassium iodide in aqueous medium also second order reaction. Now to understand all these first order, zero order, second order, try this exercise here. Okay, so decomposition of nitrogen dioxide at 300 degrees Celsius described by this equation here. Okay, and these are the data, okay, based on this reaction here. Okay, so you have to solve whether this decomposition is zero order or first order or second order. So what do we do first? Okay, remember I asked you to memorize the plot as well as the equation for each order of reaction. Okay, now let us start first with plotting ln concentration of the nitrogen dioxide versus time. So that is the curve for first order. You can try plotting zero order first. So zero order is concentration of the nitrogen dioxide versus time. So you have different concentration, nitrogen dioxide and time. So plot. Based on this data here, do you get a straight negative slope? If you don't, then it does not obey zero order. So try plotting for first order. So this is the plot for first order. Ln the concentration of nitrogen dioxide. So you have to ln the concentration. So this is the ln value, okay, versus time, okay, and see if you get a straight negative slope. But looking at this plot here, it does not look like a straight plot. So it means it's not a first order kinetic. Now try plotting for second order. So second order, this is second order, okay. So you have to calculate first 1 over nitrogen dioxide concentration, okay, and then plot versus time. Okay, so we get a straight positive slope, and this proves that this nitrogen dioxide obeys the second order kinetic. Now if you don't want to plot, you can just substitute the value of each concentration, okay, and time into the memorized formula for first order, zero order, and second order. Remember, the K constant has to be constant. Okay, so when you substitute T and concentration, okay, for zero order, you will not get the same value of K, okay, if you try at this different time. So that means it's not zero order. So if you substitute the T and concentration into the first order formula, integrated form, and your K value also will not be the same. Okay, and then try substituting the T and concentration, okay, into the integrated second order formula. You will get the same K value. Okay, so that is one way. Another approach is using the half-life method. Okay, you also have to memorize the half-life formula. So substitute it into the half-life value. Okay, but if you use half-life, you have to know the concentration of no, you just substitute it into the half-life formula, okay, for each order of reaction. Okay, for first order, zero order, first order, and second order. Okay, but still you have to know the K value. Okay, so I don't think half-life method is appropriate in this context. Okay, because it does not mention anything about half. Okay, because for half-life for zero order is A naught over 2k. For first order is 0.693 over k. For second order is 1 over k A naught. Okay, so using half-life would not be appropriate in this context unless it mention half in the question. Okay, next is higher order kinetic, third and higher order, okay, which I have explained in my earlier lecture, okay, earlier on. Okay, third and higher order are quite rare because you must ensure that the three reactant or more of the reactant collide at the same time. Okay, fractional order kinetics, okay, this is also possible. This one is possible. Okay, fractional order. Okay, if the rate of the reaction is proportional to the fractional power of the concentration of the reactant, and I have shown you a few examples of this fractional order. Okay, so this is the summary, okay, for zero order, first order, second order, the rate law, the integrated form, the unit of the rate constant, and also half-life formula. So basically you have to memorize this slide. And that concludes the first part of kinetics.